Hey, so taking all these laws and combining them, this is the combined gas law. So underwater, the pressure on a diver is greater than atmospheric pressure. The combined gas laws come from the pressure, volume, temperature relationships for gases that we've just studied. So let's use the combined gas law to calculate the final pressure, volume, or temperature of a gas when given changes in two of these properties and given the amount of gas is constant. All right, so let's try. So the combined gas law uses the pressure, volume, temperature relationship that we learned from Boyle's law, Charles' law, and Gay-Lussac's law, where the N is going to be constant. So just to remember, for Boyle's law, it was P1 times V1 equals P2 times V2. Charles' law was V1 over T1 equals V2 divided by T2. And Gay-Lussac's law was P1 over T1 equals P2 over T2. So combining all of these into one law, this is the combined gas law. So P1 times V1 over T1 equals P2 times V2 over T2. Okay, so here is again your summary when the properties that are held constant in this column, the relationship, and then again the name of the laws so we can separate them all out and how they cancel to end up giving us that final combined gas law. So, trying to do this together, a gas has a volume of 675 milliliters at 35 degrees Celsius and 646 millimeters of mercury pressure. What is the volume in milliliters of the gas at minus 95 degrees Celsius and a pressure of 802 millimeters of mercury when N is going to be constant? Okay, that was a mouthful. So let's set it up. So let's organize. So our conditions 1 are here. Our P1 is this, our V1 is this, our T1 is that, and if we figure it out in kelvins, we end up with 308 kelvins. Okay, our conditions are here. We are looking for V2, and again, the moles of the gas are going to remain the same. So let's rearrange to solve for the unknown quantity of V2. So we can rearrange this so that V2 equals V1 times P1 over P2 times T2 over T1. So step 3, let's substitute in those values, the gas law equation, and calculate. So V2 is going to be 675 milliliters times 646 milliliters mercury over 802 millimeters mercury. Millimeters of mercury are going to cancel out. Then we're going to have 178 kelvins over 308 kelvins. Kelvins cancel out, and it ends up giving us 314 milliliters. All right, so let's try it again. So pause me and come back. All right, so for the sample of helium gas, we have a volume of 0.180 liters and the pressure of 0.800 atm. And this is the temperature of 29 degrees Celsius. At one temperature in degrees Celsius, will the helium have a volume of 90.0 milliliters and a pressure of 3.2 atm. And again, remembering that N remains constant. So let's organize the data into the table of initial and final conditions. Our conditions 1 are listed here, our conditions 2 are listed here, and our T2 is going to be our unknown. So let's rearrange to solve for the unknown quantity of T2. That gives us this equation of T2 equals T1 times P2 over P1 times V2 over V1. Okay, and what does that give us? That gives us 604 kelvins minus 273 equals 331 degrees Celsius. Great job, guys.